Okay, welcome Year 9s to this first video, this introductory video for simultaneous linear equations. What I'm going to do in this video is just introduce you to what simultaneous linear equations are, show you how we could do this using a graph, but in reality we don't really use a graph generally to solve simultaneous linear equations. So just an introduction in this video, and then in the next couple of videos I'll show you how we actually solve them algebraically. So to start off with, what I've got here is an example of some simultaneous linear equations. The reason I know that they're simultaneous is there are two equations written here. And one other thing about them is I know that they're not parallel lines. Now, there's a good reason that I mention that, and that's because simultaneous linear equations, what we're essentially trying to do is we would graph these. We know that these two equations form a linear graph, and that's what you've been working on in class so far this term. When you've got two lines and you've got them on the same graph, these two lines will intersect. But of course, if they were parallel, we know that parallel lines would never ever meet. So the two lines will intersect as long as they are not parallel. Now looking at these two lines, I've chosen just a couple of really easy ones to get us started with. I know that these are not parallel, and that's because their gradients are different. Parallel lines have the same gradient. So the gradient of this first line is 1, but of the second one is -1. Therefore, I know they will intersect at a particular point. And that's essentially what we're trying to find. Whenever we're looking at simultaneous linear equations, we're focusing on where do these two lines meet. So if we were trying to solve that graphically, so what I've done is just under here set up just a really rough Cartesian plane. You can see that I've done it by hand, so it's not perfect. What we're going to do is start off by just graphing these two on the same set of axes below. Okay, so to start off with, I'll do my y equals x plus 2. Now, obviously, I can see that the y-intercept for that occurs down here at y equals 2. And of course, to get my x-intercept of this graph, I know the x-intercept occurs where y is equal to 0. So therefore, x would be equal to -2. There it is there. Now I can connect that with a straight line. Now forgive me if this doesn't work. Sometimes, well, it's not too bad. Sometimes I can't get it right on the spot just because I'm doing it on the computer. So it's not absolutely accurate, but this one is y equals x plus 2. Okay, let's graph this second one now. Use a different color. Y is equal to 6 minus x. So it's cutting the y-axis at y equals 6. I get that from the rule. There it is there. Let's get the x-intercept now. X-intercept occurs where y equals 0. So 0 equals 6 minus x. Therefore, x is equal to 6. So that's for that one there. So x is equal to 6 over here. The y-intercept we know was 6 as well. So let's get a straight line through there. Again, it's not spot on. It's close enough at the moment. So this one is y equals 6 minus x. Okay, so we have graphed the two equations on the same set of axes, and what you will see is they do meet. They do meet here. Now this point, we do give it a name. We call this the point of intersection. Another phrase we use, it's the solution. It is the solution of the simultaneous equations. And I haven't left myself enough room there. The point of intersection where the two lines meet. It is the solution of the simultaneous equation. So if you were asked to solve these two equations simultaneously or solve the simultaneous linear equations, essentially what you would be giving is this coordinate right here. Now, because I've done it on the graph and it's not perfect, it's not absolutely accurate, I haven't used grid lines, I haven't even used a ruler for this, it can be really difficult at times to read off the actual solution from the graph. But I can do it here because of the two equations that I've chosen. I know that I'm going to get integer values. I'm going to get really clear, a really clear solution for this, and that is 2, 4. So this is my point of intersection 2, 4. So what you might be thinking of is, okay, well, what happens if your point of intersection is a fraction? Well, obviously, using a graph when your point of intersection is a non-integer is not ideal. You don't want to be guessing what your point of intersection is. You do want to know exactly what is the point of intersection so that you can say, yes, I have the solution to the simultaneous equations. For that reason, the way that I've done it here, the way I have found the solution, the way I found the coordinate of the point of intersection, this is not generally how we do it. So just to make a few points, finding the solution via a graph is slow. And it's a bit tedious as well. If we had to draw a graph every time we wanted to solve these, not ideal when the solution or solutions is not an integer, so not a whole number. But to start you off, it is a good idea to see visually what it is we're talking about when we talk about this solution. Now, another thing about this solution here, 2, 4, if I go to my next page, there it is there, is that solution, what we should find, is it satisfies both of these equations. What I mean by that is if I substitute the x and y values here into both of these rules, both equations should be true. So let's have a look. I'll do my first one here. If y is equal to x plus 2, let's put the y value in, let's put the x value in, and we see, yep, 4 is equal to 4. Perfect, it works. Let's try the other one. Y is equal to 6 minus x. Substitute that value in. 4 is equal to 6 minus 2. Is that true? Yes, it is. So what we should find is the solution to the simultaneous equations the value of x and y that satisfies both of those, both equations. And yes, we do this algebraically, which, like I said, in the next video I'll show you how we generally do that. There are a couple of different methods because, of course, we can get our equations in different forms. So it is ideal to have a couple of different methods up our sleeves to work with our simultaneous equations. So just to work on this concept here, that this solution of the simultaneous equations, that point of intersection, it must satisfy both of these equations. What I'm going to do is just show you a couple of example questions. So just say, for example, you've got a question such as this: determine by substitution whether this coordinate 1, 2 is the solution to these two equations here, x plus y equals 3 and y equals x plus 1. So we just need to do a bit of substitution to check, and then we can say yes, it's the solution, or no, it is not the solution. So if we have x plus y is equal to 3 and we're considering the point 1, 2. When we put that into the equation there, we can see that yes, it works for that first equation. Let's try the other one now. What we can see is yes, this point here is the solution to these equations listed above, because both of these equations are satisfied using that point. Both of them work. This question, however, let's have a look. -1 and 6 are our x and y values. Let's have a go with this one here first. Y is equal to x plus 7. Okay, well 6 is equal to -1 plus 7. That works. However, this one here, if we have a look, -1 and 6, it does not equal 3. Okay, so what this means is this point here, it does lie on that line, but it does not lie on this line over here. It doesn't lie on that one. What this means is these two simultaneous, or these two graphs, these two lines, they must not meet at that point there. It's impossible for them to meet there because this equation over here does not even, or this line I should say, it doesn't even pass through that point there. It's impossible then for these two to meet at that point. So again, it must satisfy both of them. If it's not satisfying one of the equations, then it is not the solution. It is not the point of intersection, which is what I mentioned earlier. Okay, so I'll finish this one up right here because like I said, doing this on a graph is generally not how we would do it. It is one way to do it when you've got some, I guess, easy equations, very, very clear points of intersection, and of course an accurate graph drawn so that you can get that accurate point of intersection. In the next video, I'm going to show you one of the methods, and that method is called solving simultaneous equations via the method of substitution.